Okay, let's begin. So, we are going to finish up our discussion on approximate integrals today. We're going to finish these problems. First announcements, I guess. Test 1. That's next week. So, if you want to have a quiz, you have a test instead. That's February, what's the date? 24th. 24th. So, what you'll notice now, there is a review posted on the class website.
It's the 25th.
Alright, so that's when you go to Jhevon.org/teaching and you click on 1207. So, there are instructions there. I would say read the instructions through entirely before you actually start doing it. But I basically tell you how you want to go about studying the topics that are going to be on the test. And then I actually also posted a mock test. So that's pretty much what the test is going to look like. And so what I would say the best approach is to make sure you're actually taking the mock test as a test. So pretend you're studying for the real deal. And maybe Saturday or Sunday, actually sit down, time yourself, don't get any help, and try to actually go through the test. Don't look at it ahead of time. So you want to kind of model what it would be like to be in a test. So you want to be surprised the first time you look at it, and actually try to work through it in 50 minutes. So you'll have the entire session. It's 50 minutes long. So I already told you what topics we'll cover. Basically all of integration and approximate integrals. And I might start talking about something today, but I put that towards the bonus section. So the new stuff I talk about today won't technically be on it. But yeah. And I think that's all I want to say. So we have a test next week, unless there are questions.
Is it during recitation?
It's during the recitation. Yeah.
So I think I asked last time, but you said it was an hour, right? The test is an hour, right?
Well, 50 minutes. It's the entire recitation session.
Oh,
Yeah. So yeah, that's that. That being said, let's just move on. So, we continue with these guys. So last time we were supposed to complete problem 1 and 2 and then do problems 3. So, in problem 1, we did the trapezoid rule. I'm kind of going to skip the midpoint rule. I'm pretty much not going to ask you about that because that's like a Calc 1 topic actually. So 1C. So we're going to do the Simpsons rule. Approximate the integral from 0 to pi of the sine of x dx. And then 2, find the error associated with the above approximation. And here we're using n equals 4. And remember, for Simpsons rule, it is very important that you have an even number of dissections. For all the others, it doesn't actually matter. But for Simpsons specifically, your n needs to be an even number. You need an even number of subintervals. And for the most part, on the test, I'm going to actually give you these formulas. So you don't have to actually memorize them, you just need to know how to use them. And so, yeah, so starting on 1C. What's the first thing we want to do here when we want to do one of these guys? Yeah?
Like the little line and figure out what the x values are.
Right, and what determines what the x values are.
So, what n equals? It's the interval divided by x.
Yeah, but that's what I'm talking about. What's that called?
Delta.
Delta x. So the first thing you want to do is you want to find delta x, and that's going to tell you how to divide these guys up. Now delta x is, what's the formula?
B minus
B minus
A.
A.
b minus a over n. So that's the first thing. So we have pi minus 0 over 4. So pi over 4. Now that's going to tell you how this interval is dissected. So it's from 0 to pi, and it's cut into 4 pieces, and the length of each piece is pi over 4. That's the length. Okay. So you add pi over 4, that's the first thing. Pi over 4. Then you have 2 pi over 4s. Then you have 3 pi over 4s. Then you have 4 pi over 4s, right? And of course, the 2 pi over 4, you can simplify to pi over 2. So that's the first thing. Find what the subintervals are going to be. To do that, find your delta x, start at the a, and just add your delta x n times till you get to the b. So those are going to be the dissections. And of course, 0 here is your x0 is how we start counting. That's your x1, that's your x2, that's your x3, that's your x4. And now remember, Simpsons rule, it uses all the values, so there's none that are left out of it. So remember with the right hand and left hand rule from Calc 1, we actually left off some of them, but Simpsons is going to use everybody. And the formula, so the area under this curve is going to be approximately equal to S sub 4, which is going to be delta x over 3 times, so it's going to be f of x sub 0 plus 4 times f of x1 plus 2. So the Simpsons rule has the 4 and the 2's alternating. Starting with the 4 in the second term plus 4 x3 plus the last term x4. So that's going to be the formula. That's going to be on the sheet, which I'm going to give you. So you can memorize that if you want, but you don't have to. And now you actually just plug in these values. So our delta x is pi over 4, so I'm going to plug that in here. So I'm going to get pi over 12 times f of x0, which is pretty much just the sine function, sine of 0, plus 4 times sine of pi over 4, plus 2 times sine of pi over 2, plus 4 times sine of 3 pi over 4, plus sine of pi. Sine of 0 is 0, sine of pi is also 0. Sine of pi over 4 is radical 2 over 2. Sine of 3 pi over 4 is also radical 2 over 2. Sine of pi over 2 is 1. So this all simplifies to pi over 12 times 2 rad 2 for this part, plus 2 plus 2 rad 2 for that part. That's that. So that's pi over 12, 2 plus 4 rad 2. I guess you can think of that as pi over 6. That's your approximation for the area under that curve. Now, how good an approximation is it? Well, we want to find the error associated with the Simpsons rule. We want to find the magnitude of that. And in fact, we know that there's an upper bound for this. There's a limit on how wrong we can be using the Simpsons rule. And what was that?
K times b minus a to the 5th power over 180 times n to the 4.
Okay, now where, what does k mean in this instance? Yeah.
We just off of K, we know that the f double prime x is less than or equal to K on A to B. So we can find the double.
Is that what's for Simpsons rule?
No, it's 4.
Yeah, for Simpsons it's different. For Simpsons you need 4 derivatives.
4 derivatives.
Yeah. So k is going to be the smallest constant that you can think of that's greater than or equal to the 4th derivative on the interval. Yeah, so for the trapezoid and the midpoint, you'll need 2 derivatives. Simpson needs 4 derivatives to actually work out. Because it's a parabola, it's not being approximated by a straight line, you actually need more derivatives to match up to the curve of the parabola. So, yeah, so what we're going to first do is figure out what's a nice k to choose. We kind of already know what the answer is going to be here. So our f of x was sine of x, f prime is cosine of x, f double prime is minus sine of x, f triple prime is minus cosine of x, f to the fourth prime sine of x. So you need k so that the magnitude of sine x is always smaller than or equal to k on the interval 0 to pi. And this means k equals 1 works. Now it's not always k equals 1, and it's not even always k equals 1 if there's a trig function. It's possible to not, for that to not be the case. So for example, if I had like sine of 5x, then of course the magnitude that we're going to have down here is actually going to not be, 1 would probably not be the best one. Or if I had 7 times the sine of 5x, right? There are different magnitudes. So you actually need to go through the derivatives here and actually examine the function on the integral to make sure you can have a good number. But this one's just an easy problem because, you know, it's example 1. So this means the magnitude of the error of the answer that we just had here is going to be smaller than or equal to 1 times pi minus 0 to the 5th over 180 times n to the 4th. So our max error is pi to the 5th over 180, 4 to the 4th. So that's how much we're going to be off. And you put into your calculator if you're curious as to what the actual numbers are and how far you're actually away, but you don't need to. Like, that would be the answer for this question.
Sorry, I just had a real quick question. I'm so confused. How do we know 1 works again?
Because it's just a sine function. Because I know about this function. Right? Sine is just this function. And it's always below, it's always 1 or less. Right? In absolute value, it's always smaller than or equal to 1. The particular function is what matters.
Oh, I see. So just like the
Yeah.
range?
Yeah, so I need to know what range is going to work here. Maybe maybe example 3 will be a little bit more insightful in that regard. How many subintervals are needed to make sure the error associated with the trapezoid rule in approximating that is less than 1 over 100? Okay. Now again, this integral isn't terribly difficult because I don't want you to focus on how terrible the integral looks. I want you to focus on the actual approximations that we're doing. So we are going to, this is an example 3, we're approximating the integral from 1 up to 2 of 1 over x by the trapezoid rule, right? Then the question is, how many subintervals are needed? So that our error is less than 1 over 100. So that's the question. So, something like this is important in what sense? Suppose I have an integral that is really important that I know what that integral is, but it's very difficult. It's not 1 over x, it's something really crazy that I don't know the antiderivative for it, I don't know an integration technique that can do it, no one knows an integration technique, and maybe we know for a fact that the antiderivative does not exist, but I still need to find the error under the curve on some interval. It's very important, right? End of the world if I don't find this integral. What can I do? Well, I can start approximating numerically, right? So with the numerical method, you don't need to really know how to integrate. All you need to do is be able to find the area under a trapezoid, which we know how to do that. So I need to approximate this, and I want to do the area under the trapezoids to actually approximate that. Now here's the thing. How many subintervals do I need in order so that my error is within a certain tolerance, right? So you have this integral that you really need, you don't know how to approximate it, you don't know how to actually do it directly, so you said, all right, we're going to approximate it. But now you're going to be like, well, what do I tell the computer? Take n equals what? What is going to be good enough as an approximation? Do I need 1 trapezoid? Do I need 2 trapezoid? Do I need 1,000 trapezoids? Right? This is an important question because you don't want to just have your computer running off finding areas of trapezoids without any end in sight, right? There's going to be a goal in your mind of how good you want the approximation to be. And so let's say for our purposes we just determined, you know what, if we're off by more than 1/100th, that's bad. Just make sure our error is less than that, right? So whatever machine I want to plug this into, it takes 2 decimal places, so I want to be accurate to 2 decimal places. So that's what you want, right? So I want to approximate this and make sure that whatever answer I get, the first 2 decimal places are right. I don't care about the 3rd decimal place onwards, right? What does n need to be? That's another way you can phrase this. What does n need to be? Right? So if I want to use trapezoid rule to do that, get that error, how do I choose n? How many subintervals do I need here? What do you guys think? Yeah.
I think we can first start out, we know that this is trapezoid rule, so we know that the denominator for the error is 12n squared.
Okay.
And then we know b minus a is just 1. And then we know the value for k.
Do we?
Well, we could choose a value for k.
What value?
We could look at the range from 1/x, so,
Is that how you choose k?
I mean, you could, for this one, it's the two derivatives.
2 derivatives.
So the first derivative is ln x.
So, no, the antiderivative is ln x. Okay, so what we're going to do is we're going to use the error formula. So I know the error associated with the trapezoid rule. I know an upper bound for that, right? What is that formula? It's k times b minus a to the what?
Cubed.
Over 12n squared?
Yeah.
Is that a squared?
Yeah.
Okay, right. So I know whenever I do the trapezoid rule, that's the guy that's going to tell me the error. So all you need to do now is just like, we need this guy to be less than 1/100. That's all I need. So the b I know, that's 2. The a I know, that's 1. The n I don't know. The whole point of this exercise is to figure out what n is. But in order to actually find n, I need to be able to find the k. So what is the restriction on k?
Has to be more than the second derivative of x.
It's an upper bound for the second derivative on the interval 1 to 2. So this is not so bad, but it's not as silly as just having a sine x, where 1 is always going to be the number that works. This one have to be a little bit more. So our f of x is 1/x. What is our f prime?
Negative 1/x squared.
And what is our f double prime?
2/x.
2/x cubed. So we want the magnitude of 2/x cubed to be less than or equal to k on the interval 1, 2. What is a good k to pick?
2.
The max for 2 over x cubed is, on that interval is 2, right?
Right, you would choose k equals 2 in this case. Why is that? Well, if you look at 2 over x cubed, right, that guy looks like this. He's falling the whole time on this side, right? So between 1 and 2, this function will actually be the largest it possibly is at the left endpoint, right? That is going to occur, the y value is going to be 2. At 2, it'll decrease to a value of a quarter, right? So the smallest constant that I can think of that's going to be larger than this function everywhere on this interval would just be the constant value 2, right? On that interval, 2 is going to be a minimal value that's larger than everyone on that value. So k equals 2 would be the guy I would pick. So this means we need 2 times 2 minus 1 cubed over 12n squared should be less than 1 over 100. And at this point now I'm just going to solve for n. This means I can take the reciprocal of both sides, 12n squared, this is over 2. And of course if I take the reciprocal, that's going to turn around because both of these numbers are positive. So this means I would need 12n squared to be larger than 200, which means I need my n to be larger than, well, 200 over 12 square rooted. Now the question is that a whole number? I don't know. What we can do then is choose n equals something like the ceiling function. You may have seen this function mentioned before, maybe not, but I'll just tell you what it is right now. So you write this little symbol here, and you write that guy inside. Right? Now what this symbol means, this is called the ceiling function. It's the smallest integer greater than that number. So note, if you look at f of x equals this symbol here, this is called the ceiling function. And it's equal to the smallest integer greater than x. That is basically round up all the time, round up. Right, so if the ceiling function of 2.1 is 3, the ceiling function of 17.9 is 18. Right? The ceiling function of pi is 4. Right? You always round up to the next biggest integer. Right? So if this isn't an integer, I'll just round up to the next biggest one. So if this is 12.3, whatever that is, I don't know if it's 12.3, but just saying, then I would choose n equals 4. Tell the computer do it for 12.3. I would choose n equals 13. Tell the computer to use 13 subintervals. Right? Yeah.
If something like this was on the test, would you take points off if we don't put the ceiling function?
I wouldn't take off a lot of points, maybe 1 point.
Oh, so it's completely required.
Yeah, because by definition n is an integer. So if you just tell me it's some strange thing,
Okay.
right? This could be a decimal, right? To make sure it's an integer, you do like a ceiling function. What is that actually? Square root of 200 over 12, what's that? Square root. Oh, that's not that big, that's 4.08, which means to get this to work, I just need 5 subintervals. So a trapezoid rule is going to approximate this pretty accurately with just 5 subintervals. After 5 subintervals, I'm within 2 decimal places of the real answer, which isn't totally surprising. I mean, the graph does look like this, I mean, it is the kind of thing where a trapezoid would fit it very nicely, you know what I mean? Because it will just slant down. So, yeah, it shouldn't take a lot to get that. With rectangles, with like this is curving down. If I have a rectangles where the tops had to be straight, right? It'll take a lot more rectangles to actually fill in those gaps. So if I were doing like the left-hand rule or the right-hand rule, I'd need more. But with the trapezoid rule in this case, 5 trapezoids is going to do it. 5 trapezoids gets me within 2 decimal places. Right? So I can know ahead of time that if I need to approximate something, I can know ahead of time, depending on which rule I want to use, I can know exactly how far I would have to take it to be accurate to within some tolerance. And that's something that happens all the time. That's an important thing. Especially in engineering, these kinds of things come up all the time. And at that point, it's like a matter of safety a lot of the times. You want to build this bridge, how much weight can it hold? As long as we're less than 10,000 people on this bridge, we're good. Of course, with engineering, you of course over-engineer. You don't put the capacity saying 10,000 when it's actually 10,000. Like, if an engineer is convinced that his bridge can only hold 3,000 people, he says the capacity is 10,000. Just in case you have like people going overboard. So yeah, in those elevators when you have to, oh, max capacity is 200 pounds. No, it's actually more than that. So they want to make sure they don't get sued. So, yeah. So problem 4. So this is just set up. Midpoint approximation. Again, it's a Calc 1 thing, approximation. But it has little nuances that I want to make sure that you remember. Over the integral, again 1 to 2 of the square root of 1 plus x cubed dx and equals. Now there's a guy that's super hard to integrate. Don't really have a way to integrate that. So maybe you do, but I don't want to think about it. So I have an midpoint approximation for that. So first step, find your delta x. It's going to be b minus a over n, 2 minus 1 over 4, so it's a quarter. So that means your interval between 1 and 2 is cut into 4 slices, where each one is a quarter. So this is 4 over 4 plus 1 over 4, 5 over 4, plus 1 over 4, 6 over 4, plus 1 over 4, 7 over 4, plus 1 over 4, 8 over 4. That gives you 2. So those are the guys. So which one of these guys do you want to pick for this approximation? How do you set up the midpoint approximation? What are the x values that are selected? Yeah?
They're just in between.
Yeah, it's none of these guys. It's the guys in between them, right? So the midpoint approximation goes with the guys in the middle. It's called the midpoint. So these are the guys we actually want, the guys right smack dab in the middle. Now, how do we actually find those? Well, for the first one, it's found by taking the average of these two. So your x naught star or x naught bar, sometimes we use it, is going to be just take 5 over 4 plus 1 all over 2. So it's 9 over 4 all over 2. So that's 9 over 8. So that's going to be the first guy here, 9 over 8. Now, once you find the first guy, you just keep adding the same delta x, right? So you keep adding a quarter to that. A quarter. What?
Sorry. No.
Yeah, so a quarter is going to just be 2 over 8, so add 2 over 8 to that, 11 over 8, add 2 over 8 to that, 13 over 8, add 2 over 8 to that, 15 over 8. And those are the numbers we picked. So the midpoint approximation, so this is 1 up to 2 of the square root of 1 plus x cubed dx. this is approximately equal to delta x times f of 9 over 8 plus f of 11 over 8 plus f of 13 over 8 plus f of 15 over 8. Delta x is a quarter, so that's going to be the square root of 1 plus 9 over 8 cubed plus the square root of 1 plus 11 over 8 cubed plus the square root of 1 plus 13 over 8 cubed plus the square root of 1 plus 15 over 8 cubed. And just want to set up, I don't want to actually find the exact answer, that's good enough. Right. So all of these problems in terms of the actual approximation, it's pretty much this strategy here. Find the x values that you want to select, plug into the right formula according to this page over here, and if I follow up and ask you, hey, how good is this approximation? Then use the error formulas on this page. And if I give you the n, you just plug that in, find the k value that works, and you're good. If I ask you, how many subintervals do I need to get the approximation to be this good, then you do what we did in problem 3. Yeah.
So how do you find the k for the error for the midpoint rule? Is it the first derivative
No, it's the second derivative.
for the midpoint?
Yes.
Okay.
So it says for the above, the k is this. Right. It means it includes both of those. Right. The Simpsons rule is the one that means a lot. Okay, that's basically it. Do you have other questions? I don't know if I should start another topic right now.
Oh, I have a question.
Unless there are more questions. Yeah.
Sorry, you're gonna, on the exam, are you gonna ask a question about errors?
Yeah.
Okay, so there will be, okay.
Yep, so I'll definitely ask you to approximate something and then talk about the errors. Yeah. So any question of any of these 4 types is possible. So I'm definitely going to ask you to approximate something using either the trapezoid or the Simpsons rule. I'll definitely follow up with an error question, but I'm not sure I'll follow up with an error question more like problem 2 or problem 3. Maybe I'll do problem 3. Maybe both. I think we can do both.
No, too hard, too directional.
Yeah, so I mean, the next few things I want to do are going to kind of be different, so I probably don't want to start now. That being said, we have been moving relatively slow, a little bit slower than I wanted to, so eventually I'm going to pick up the pace. So, you know, starting next week, hopefully you guys have acclimatized to the pressure of this class and you'll be able to increase your output further, but I think I'll stop there for now. So your test is going to cover everything up to here. Everything we've done up to here. And yeah, like I said, I posted a mock exam with some instructions, so go through that. If you have any issues, you can reach out to me and deal with it from there. I think we'll stop here.
Sorry, this one's the exam, right? This is the exam.
Yeah, the formulas for approximation is, that's the only thing I'm giving you. So everything else you have to have memorized. All the other rules you have to have memorized. But these I'll give you in the exam.
Approximation and error formulas? Or
Yeah, I'll give you both sets of formulas. Everything for this topic.